This video contains the solution for 2011 AP Physics C Mechanics, problem number 3. The key to this problem, especially the first two parts, is understanding what they're telling us here, that the motion of a torsion pendulum is analogous to the motion of a mass on an oscillating spring. So here, torque equals negative some constant beta times theta. That's like, so they're giving us torque is equal to negative beta times theta, and they're saying that's like a mass on an oscillating spring, where the spring constant is k, and x is the displacement. And we know from rotational mechanics that force is analogous to torque, displacement is analogous to angular displacement. So this actually looks very similar. So let's see if we can follow through in a similar way. Here in part A, they want us to write but not to solve the differential equation that could be used to determine the angular displacement theta of the torsion pendulum as a function of time. That means we're looking at kinematics type variables. So we have torque equals minus beta times theta. Well, torque is equal to force equals mass times acceleration. Torque is equal to moment of inertia is the rotational analog of mass times angular acceleration. So let's substitute that here. And then our rotational kinematics equations tell us that this is the second derivative of this. So we can substitute second derivative of theta for angular acceleration. And that's it. I mean, you can move the I over there if you want to, but it's that is the differential equation that you could solve. They're not asking us to, for theta. Excuse me. Theta as a function of t. B, using the analogy to a mass oscillating in a spring, determine the period. Well, period is equal to 2 pi times the square root of m over k for an oscillating spring. So here it's a matter of figuring out what these should be. And let's see, the k is clearly the b, right? And if we look at what we did here, we've solved this kind of situation before when we had a spring, when we first studied simple harmonic motion. So if we had done the same thing here, force is equal to mass times acceleration, and acceleration is the second derivative of position with respect to time. So that would have been the differential equation. And so mass is analogous to moment of inertia, so that's and the k is analogous to b. Well, that's it. So period is equal to 2 pi times the square root. Mass is in the same place as moment of inertia, and the b is in the same place as the k, or the beta. So that's the period. It's of that same form, 2 pi times the square root of something. You know, the physical pendulum, we know a simple pendulum, and this is the equation for a torsion pendulum. For part C, on the graph below, plot the data points and draw a straight line that best represents the data. So the data points that they want, oh, here we go. To determine the torsion, disks of different known values are attached to the rod, and data below are obtained from the resulting oscillations. So if we want to get a straight line, I think what we need to plot is t squared is equal to 4 pi squared over beta times the moment of inertia. This is like our y equals mx, where this will be the m, that's what we want on the y-axis, that's what we want on the x-axis. So, oh hey, they didn't even leave that up to us. They told us right here to plot those things. I'll leave you to plot that, but I would like to point out that whatever the plot looks like, it does not go through the origin, and that's important. So I'm just going to go ahead and do the line of best fit. So my x values are the I values. Let me get the calculator up here where you can see it. Let's see if you can see the screen. I think you can see that okay. So let's go into stat. Oops. Stat edit. Let's clear list 1 and clear list 2. Okay, so for my x values, I want the i's at 0.025, 0.036, 0.049, 0.064, and 0.081. So those are all squares, funny enough. 25, 36, 49, 64, and 81. And then the t squared, we want those in the y values. So we have 5, 7.2, 8.7, 11.1, and 12.9. And then we'll go stat, calculate, get our line of best fit. And it looks like the y-intercept is about 100, the slope is about 140, and the y-intercept is about 1.85. So the equation for the line would be, part D, would be t squared is equal to 140 times the moment of inertia plus 1.85. And I'm not sure, they might like this as y equals mx plus b. That's the equation for the line, but those are the actual variables, so maybe they would like y equals 140x plus 1.85. That is our regression line. And in E, calculate the torsion constant beta. Well, we knew that our slope, 140, was supposed to be equal to 4 pi squared over beta. So 4 pi squared over beta. So beta should be 4 pi squared over 140, which is about 0.282. And we really should put units on that. And if we think about what that beta is, it would have units of torque divided by an angle. So that would be torque is force times radius, so that's kilogram meters per second squared times radius. So kilogram meter squared second squared, I think, would be the units for that. And last part, what's the physical significance of the intercept of the line? Well, it didn't come down to 0. It was about 1.85, and that's the period squared. So the square root of 1.85, right, since that's a period squared, would be, let's see, that's when the moment of inertia went down to 0. So in other words, no disk. So that would be period of oscillation of the rod with no disc. As if you gave the rod a little tweak, it would start to oscillate back and forth, even if there were no rod on it. So that's that.